Hello, welcome to our Geology Brown Bag Chautauqua series. I am Carolina Londoño Michel. I am Geoscience faculty here at Chandler-Gilbert Community College. CGC is the traditional homelands of the Akimel Oldham River people, and it's also home to the Piposh people. They now live in the Gila River Indian community, which is east to our CGC campuses. And today we're gonna talk about the role of phosphorus and the significance of discoveries in Venus. We have a very special guest today. We have Dr. Hilairy Hartnett, who is jointly appointed in the School of Earth and Space Exploration and Molecular Sciences at Arizona State University. She is a seagoing oceanographer and astrobiologist who investigates the transfer of energy and elements between biological and geochemical systems on Earth and also on exoplanets, other planets. And very, very interestingly, lately she is developing approaches for building consensus among scientists, technologists, governance, and stakeholders around planetary scale climate interventions. And that is a topic for another talk that we hope to have. But she's fundamentally an interdisciplinarian, and so often surprised by the things that she now includes among her expertise. We are very honored to have you here today, Hilairy. For our students, thank you very much. Please post questions on the chat, and without further ado, please take it away.
Thank you so much, Carolina. I am delighted to be here today and to talk to you all. So I think there are my slides. Okay, great. So like Carolina said, I'm going to talk to you today about the importance of phosphorus for astrobiology and about recent discoveries on Venus that raise very tantalizing questions about what's going on in our nearest neighbor planet. Like Carolina said, I have a joint appointment both in Earth and Space Exploration, which is geology, and in molecular sciences, which is chemistry and biochemistry. And it's important for me to remember to tell you that all of our work happens because we have funding from federal agencies, including NASA and the National Science Foundation. And while I'm the only author on this talk, I have colleagues from the Nexus project, which studies exoplanetary ecosystems. And I have to thank the students from my lab, who you'll see a little bit more of in a minute. So I am an oceanographer. My PhD is in oceanography, but I am living here in Arizona. And so much of my research revolves around aquatic systems on land, as well as oceanographic systems, so lakes, rivers, and streams, hot springs. I'm interested in how organisms make use of the chemistry of their environments in order to survive and thrive. And it turns out those kinds of research questions are really important for astrobiology because they help us to know what's possible in unusual ecosystems. This is my lab group. We are the CANDY lab, the Carbon and Nitrogen Dynamics lab, and they do all the hard work to make science happen. And I can't do anything without them. And my students are both graduate students and undergraduates from several different departments. And so they have backgrounds in engineering, in chemistry, and biology, and geology as well. And I do want to remember to thank Natalie Hinkle, who I don't have a picture of, but she's my astrophysicist colleague who really has transformed the way I think about elements in the solar system and in the universe. And you'll see more of what we're doing with that in a minute. So let's get started. I'm going to go through this outline so you kind of know the roadmap. We're going to talk basically what's the big deal about Venus. If you want to put it into two points, phosphine, a molecule that has phosphorus in it, was discovered, and that got published in September of this year. And then phosphine, that same molecule, was highly disputed, and that happened in October. So it's been kind of a busy couple of months for phosphorus and Venus. And then the second part of the talk, I'm going to talk about elements in stars and planets, why we care about, say, phosphorus. And it turns out we're missing information about really important elements for understanding life and astrobiology. Phosphorus is one of those elements. And at the very end, I'm going to tell you about a project that we're starting to see if we can get money to build a new telescope that will specifically measure these biologically important elements. So why phosphorus? Well, phosphorus is critical for life, right? All of our DNA has phosphorus in it. All of our energy metabolism is based on NADPH, and that P is phosphorus. And so our genetic code and our energy currency for cells is based on phosphorus. So if we're looking for life in the solar system or life in the universe, which is what astrobiology is all about, we have a real problem in that phosphorus is critical for life and we know almost nothing about it. We don't measure it very well, and we don't have good models even for why certain molecules might be formed in certain places. So I think phosphorus is potentially the most important element for life in the universe, and we don't know anything about it. So, Venus. Venus is our nearest neighbor from a planet standpoint, and you could argue that Venus is just like Earth, but there are aspects of Venus that suggest that it's really kind of a distant cousin. And strangely, even though it's the closest planet to us, we know almost nothing about its details. In fact, a lot of what we know about Venus we've known for 20, 30, maybe even longer years, and we haven't been back to Venus in a very long time. So this is an actual photograph of Venus from a spacecraft. And the first thing you notice is it's super cloudy, right? You can't see the surface at all because it's got thick clouds. This table, and you don't have to read all the things in this table, compares things we know about Venus in this column with things we know about Earth in this column. And it turns out, for instance, Venus and Earth are close to the same size. Venus is a little smaller, both in terms of how much it weighs. This is in 10 to the 24 kilograms. The planets are very big. Its radius, right? How the size of the planet in terms of distance. The density is about the same, and that's not surprising because basically the rocks are very similar, right? Venus and Earth, at least at the surface, are both composed of basalt, right, which is a volcanic rock, granite, which is more prevalent on the Earth, but is also an igneous rock, and a bunch of altered materials. But that's about where the similarities end. We're same size, not too far apart, but those clouds make a huge difference to the surface conditions at Venus. The surface temperature on Venus is 465 C. That's extremely hot, right? The surface temperature on average on Earth is 15 degrees C. And most of us don't think about temperature in Celsius all the time. A really hot day here in Phoenix is only 40 degrees C. So this is 100 times hotter than the hottest day in Phoenix. So, okay, it's boiling hot. The other thing is pressure. The pressure at sea level on Earth is 1 bar. The pressure at the surface on Venus is 90 bar. And so that thick atmosphere is creating huge pressure at the surface. And so if you were, say, a cell, not only would you be boiled to death at the surface, but you'd be squished completely flat because the pressure is so high. Those clouds on Venus are mostly an atmosphere of carbon dioxide. We don't have very much carbon dioxide. There's a little bit of nitrogen. We have a lot of nitrogen. There's no oxygen in Venus, so obviously it wouldn't be so great for us. And the clouds are not made of water like ours. The clouds on Venus are made of sulfuric acid. That is not terribly congenial, right? So mostly we do not consider the surface of Venus to be very habitable. However, if you go up in the atmosphere high enough, pressure is lower, the temperature is lower, And there is a point in the atmosphere where it might be about the same temperature and pressure as we see on Earth. And so that has led to the idea that if there were to be life on Venus, maybe it could live in the clouds. And that idea has been around for a very long time. So the big deal is this new paper that appeared like early October, late September, in Nature Astronomy. This is what's called a high impact journal. If you publish in Nature Astronomy, it has a lot of scientific weight. And what they discovered, and this is a large team of scientists from many different institutions, is that phosphine gas, which is a gas that has phosphorus, and I'll tell you a little bit more about it in a second, was detected in the cloud decks of Venus. Well, phosphine on Earth is only produced by bacteria. There are very few processes that make phosphine that are just geology or chemistry. It's always produced by bacteria. And they go on in the paper to say that it's really hard to explain where this phosphine would come from based on the known geochemical processes on Venus. So it could be produced by biology. They never say it is, but they do suggest that they can't explain it based just on geochemistry. So this is what we would call it in the astrobiology business is a biosignature, something that's produced by biology that's probably not produced by chemistry or geology. But phosphine's a pretty wacky idea for a biosignature. Here's phosphine. It has 1 phosphorus and 3 hydrogens. And the problem with phosphine is that it's a highly toxic gas. Okay, so you want an indicator of life that's actually super toxic. That's a little weird. It's also very rare. On the Earth, it's hard to detect, but that's partly because it's very reactive with oxygen. And if there's oxygen around, this phosphine is going to react and it's going to become phosphate, which is not toxic. And it doesn't last very long. And so in order to find it in the atmosphere, you have to make enough of it that it will build up and stick around. So this little cartoon here comes from another paper that those authors wrote. And you don't need to know the details of it, but basically they have this kind of complex hand-waving model for why there could be an ecosystem in the clouds. And it has to be up in the clouds, not at the surface, because remember, the surface is super hot, in order to have a reasonable temperature and pressure. But there's no geochemical way to make phosphine up in the clouds. So if it has to be so it's in the clouds, that's where they measured it. It sticks around long enough that they know it's there. And so they have to sort of produce a model, right? An explanation for an ecosystem that could be in the clouds. And so they have bacteria living on aerosol particles, and they rise up in the mornings when the temperature is high, and they sink back down when the temperature is low, and a bunch of fancy chemistry happens. It's kind of a just so story. They detected it, and so they have to explain how it's there, and this is how they did it. But let's remember, phosphine is super toxic. It's very rare, and it turns out it reacts with light from the sun to break down. So they don't have a way to explain why it should be there except for biology. Well, this is super exciting, right? We have no evidence for life anywhere else in the solar system except on Earth. And if phosphine is made by microorganisms and we found it on Venus, it's very tantalizing to say it could be made by life on Venus. So this paper is from a bunch of astrophysicists who made some very challenging measurements. If it's correct, it's super exciting. So let's look at what they did right, why we might want to believe their data, and then at some things that might make us skeptical. So the first thing they did right, they measured the signal for this gas in different telescopes in different years. So they've confirmed the measurement with a completely independent set of measures on a different instrument. So that's quite cool. They have this model that explains the amount of phosphine that they detect. And they are very careful to say that it could be produced by a geochemical process that we don't really understand yet, and that it's not proof of life, but that it's interesting. So they were careful scientists who did what they could to replicate their result, and they're not over-interpreting their data. These are all good. But there are some reasons to be skeptical. This measurement that they made is what's called a single line detection. When you look at the atmospheric spectra with a telescope spectrograph, when you get absorption in the spectrum, that's this dip in this squiggly line, the wavelength at which that absorption happens is specific to a specific molecule. Usually, molecules have absorption at many different lines, and so you want to have multiple lines in the spectrum to detect, sorry, you can't see my fingers, to ensure that your detection is what you think it is. If you only have one line, it's very hard to say for sure that it's confirmed. So this makes the astrophysical community very skeptical. If you don't have multiple lines, it's a little hard to say. The other cause for skepticism is that the signal to noise ratio is very poor. In other words, the signal is very, very weak. It's like this really faint shadow of a signal. And while they do a couple of models, that's these red lines, to explain that it's there, the reality is that this signal is only at the 4th decimal place. It's a very small signal from one line that they're making a big interpretation of. So that's a challenge. It doesn't mean they're wrong, but it means that there are some things that you would like as a scientist to have better confirmation of. So remember I said it was detected and then it was disputed. Well, the dispute is the natural next step in the scientific process, right? You want to be able to have other scientists reproduce your results. So now there's a bunch of controversy. Venus is dead. Possible biosignature isn't there. No phosphine in the atmosphere of Venus. This is in an astrobiology website. Promising sign of life on Venus might not exist. This was in National Geographic, and these all have kind of late October dates. It turns out these news stories are all about the same follow-up paper from a different group of scientists. And the different group of scientists is raising questions about how the data were processed, those models, those squiggly red lines that trace the pattern of the signal. And those are important questions to raise, right? These are all scientists who work with the same telescopes, who are experts in the spectroscopy that are used for these things, but they're coming to a different interpretation of the signal. So what's going on right now is that scientists are working to confirm that detection of a signal that they know is phosphine. It turns out the phosphine line or signal is very close to a signal for something called sulfur dioxide, SO2. Sulfur dioxide is easy to explain in the Venus atmosphere because it comes from sulfuric acid and photochemistry, light from the sun. But what's really exciting is that the scientists who wrote the first paper and the scientists who are raising questions about how the data were processed are working together. Everybody is excited to figure out if it's right? And that's exactly the way science works. You make a discovery, other people test it, you go back and forth to see if you agree with the original discovery or if the tests don't follow up. And so this is really, we're watching an important scientific discovery play out in the real world, right? Real-time science. So it's quite exciting. I think it's great that everybody wants to know more about this phosphine signal and about other chemicals in the Venus atmosphere. Here's another beautiful picture of Venus. This one has sort of a false color to look at the chemical composition of the clouds. Even without phosphine, right? This biosignature gas, biosignature of something that would kill things. Venus is really important, right? We need to understand better how planets form, why they're so different, right? Earth and Venus have very similar characteristics and formed in the same disk of gas and dust around the same sun, and yet they're really different. And so what we need to know is not only is there life on these planets, but really how do planets work? How are we going to look at exoplanets around other stars and make predictions about what they could be like? Well, we have to study a lot of different kinds of planets, and Venus is an important one to add to that list of planets to look at, right? We study Mars all the time. But there are a lot of people advocating for a future Venus mission to get a handle on a third planet in our solar system that's still a rocky planet like the Earth, that has water present, that has similar chemicals in the atmosphere, though in different abundances. But it's a really important part of what we're calling a field now of planetology, right? The study of planets, whether there's life or biosignatures or not. So I think the future for Venus is rich and important for understanding our own solar system and the planets around other stars. So the next thing I'm going to do is I'm going to tell you a little bit about what we're doing now to study elements like phosphorus for exoplanets, planets around other stars. And it turns out when we want to understand elements, we have to understand elements when we want to understand elements in planets, we have to look at the stars. And I'll explain why. Exoplanets themselves are very, very hard to study. They're really far away, really, really far away. With the current telescopes we have, we basically only learn about how much they weigh and how big they are, what we call mass and radius, if we're lucky. And we know almost nothing else about them because they're so small compared to their stars. If you're an astrobiologist like me, you really want to know, are those planets habitable? Could anything live there? What sorts of ecosystems might they have? And the astronomers can basically tell us how much it weighs and how big it is. So we make educated guesses. Rocky planets, like the Earth, I'm going to say are sometimes habitable. Earth's great, but Mars and Venus are both rocky planets, and we know they're not terribly habitable. Gas giants like Jupiter, probably not habitable, right? Super cold, mostly hydrogen, also with very high pressure. We don't think that they're likely to be habitable. We have icy bodies in our solar system. This is the moon of Europa. If it has an ocean underneath its ice and it has hydrothermal systems that are hot, it could be habitable. But for an exoplanet, at best we can, and this is a very fancy direct imaging picture where they had to block out the light from the star to see this little planet. It's anybody's guess what that planet is like. And there could be planets that we don't even have examples of in our own solar system, so we can't even begin to guess. When we think about looking for life on other planets in solar systems that are not like ours, we start with this idea called the habitable zone. Where might there be liquid water? And so for our own solar system, Mercury is not in the habitable zone, this green band. Venus, Earth, and Mars are all in the habitable zone, but only Earth has life that we know about. And it's mostly defined by liquid water. But we just got really excited about a chemical detection on Venus. And it turns out the habitable zone is not the whole picture. The composition, the chemistry of those planets is going to matter. And we can't measure the planets directly. So we have to assume the planets are going to look like their stars. And this is why I went straight to cartoon land, because we don't have good data yet. We have some data. We measure the elements in the stars, and there's a catalog of these elements. It's called the Hypatia Catalog, and my colleague Natalie, remember Natalie? She's the person who developed this catalog and maintains it. It has element abundances for nearby stars, and it's actually quite a large database. Hypatia was the librarian at Alexandria, if you want to tie this back to your historical knowledge. So we measure elements in stars, lots of them. And so this bar chart has the elements along the x-axis, and the number of stars that have that measurement. And they're presented as a ratio to hydrogen because that's the way the astrophysicists want to talk about it. And the catalog has 6,000, almost 7,000 stars in it now. And we've measured something like 70 different elements. Many of these elements are rock-forming elements. Magnesium, silicon, calcium, potassium are elements in rocks. And some of them, there's lots of data, right? 5,000 or more stars with a measurement of silicon and magnesium and calcium. Potassium, on the other hand, there's only 360 stars that we even have data for. That makes it a little more challenging. Some of them are bioessential elements. There's like 4,000 stars with carbon data, 1,500 stars with nitrogen. And there's my favorite, phosphorus. There's only 90 stars with phosphorus data in the entire catalog. It's partly because phosphorus is hard to measure, and I'll come back to that. These elements are the ingredients for making molecules, right? If we want to make chlorophyll, which is used for photosynthesis, we need to have all the elements that make up chlorophyll. As an example, for those of you who are not chemists, it's like a recipe for cake, right? This particular cake needs sugar, butter, chocolate, flour, eggs, and milk. Eggs could be the limiting ingredient. If you don't have 2 eggs, you can't make the cake. If you have 3 eggs, you can still only make 1 cake because you would need 4 to make 2. So this idea of a limiting ingredient or a limiting nutrient is an important concept in biology. And I think it's going to be important to think about it for stars and planets. If you wanted to make plankton, right, little algae, via photosynthesis, you could write an equation for photosynthesis. You don't have to worry about what this equation says, but you need 106 carbons, 16 nitrates, and 1 phosphate in order to make a molecule of plankton, which is a weird concept. But you can imagine this as being like the flour and the eggs and the milk, right? In this particular equation, the phosphate is the limiting reagent. If you don't have phosphate, you cannot conduct photosynthesis. It's absolutely critical. So on Earth, we can calculate the ratios of these important biological elements, carbon, nitrogen, phosphorus, which were the 3 I highlighted before. And there's that same ratio I told you for plankton, 106 to 16 to 1. That's actually a very famous ratio in ecology that was named after a guy named Redfield. I can do the same calculation for Earth's crust, right? I can go into the scientific literature and find out the average amount of carbon, nitrogen, phosphorus in crust rocks. And it turns out this is those proportions, and they're very different from plankton, right? If you normalize it all to phosphorus, there's way less nitrogen in rocks than there is in plankton. Being unafraid, I decided to do this for a whole lot of geological components. This is Mars, what we call bulk silicate Mars. And it turns out Mars doesn't look a whole lot different from Earth, but it has less nitrogen and less carbon for every phosphorus than the Earth. This has to do with differences in the way the planets differentiate when they form. Because we have data for the stars from the Hypatia Catalog, we can also calculate these numbers for stars. And our own sun, turns out, has a lot of carbon compared to nitrogen and phosphorus. That's really interesting. But is the sun a typical star, or does the sun look different from other stars? Well, I have the Hypatia Catalog with thousands of stars I can compare to. Nearby stars from the Hypatia Catalog have less carbon and less nitrogen than our own sun. So now you can ask a really interesting question. Is our sun different enough that our solar system isn't a typical planetary system? Is the Earth unique? Is that why we think it's possible we're the only planet with life? Or are lots of different stars capable of forming planets that have life-supporting ratios? Super cool questions that we don't know the answers to yet. I'm going to show you a little of the Hypatia data just because I think it's important to look at data. So this is a plot of nitrogen, carbon, and silicon. They're the molar ratios, similar to what I showed in the table. Carbon to silicon ratio on the bottom. Sorry, my laser pointer's not quite up to speed. And nitrogen to silicon on the y-axis. All the circles, green ones and black ones, are stars. The black ones happen to be stars that have planets. And what you see is that those two sets of data basically lie right on top of each other. So the stars and the stars with planets look about the same. Our sun, however, is way over here. It's not right in the center of the batch of stars. So maybe our sun is a little different. And it turns out the values that you calculate for Plankton are down here. And all of the planet data are crammed way down here near the origin. So stars and planets don't look like each other. And our sun is somewhat unusual. And this is for nitrogen and carbon and silicon, where we have a lot of data, right? There's about 1,400 stars that I could do this calculation for. But I started out talking about phosphorus, right? So I'm sorry, this is a complicated figure. Let's start with the big one on the bottom. Now I have nitrogen-carbon ratio on the y-axis and phosphorus-carbon ratio on the x-axis. And all the stars are way over here with very low values of phosphorus to carbon. They're spread out on the nitrogen axis, but they have hardly any phosphorus. And our sun is right there, and the plankton are just off this line a little bit. But the Earth and the Earth's crust and the Mars data are way out here. I had to stretch this graph out a lot. Mars has a ton of phosphorus. And the Earth, whether you look at the crust or the whole Earth, still has a lot more phosphorus than the stars. So that's interesting. It means that the planets have quite different phosphorus values from each other and from their sun, or our sun. But let's zoom in on this part of the axis. And so now this inset has the same y-axis, but now I only have this tiny little bit of the phosphorus axis. Here are all the stars, and here's our sun. You remember the last figure had so many stars that you could see a cloud that was really interpretable. This plot only has 60 stars. It's really hard to do statistics on astrophysical objects with only 60 stars, right? There's lots of uncertainty. This is an error bar that tells you how well we know these ratios in both directions. And so you want more data in order to be able to say statistically the average value is whatever it is. And we can't do that for phosphorus yet. This is a real problem if phosphorus is super important for life. So why is there so little phosphorus data? Well, the phosphorus lines are inherently weak. They're difficult to detect. That was true for the phosphine on Venus, too. They also happen to be measured in a part of the electromagnetic spectrum that very few of the high-resolution spectrographs or telescopes cover. So there's not that many ways to do it. And on top of all of that, you have to measure it from a space telescope. You can't measure it from the ground because this spectral range is blocked by water in the atmosphere. Okay, so now the element I care about most, that's super important for biology, is very hard to measure. No wonder there's no data. Well, I can ask for anything, right? I want my own telescope. Wouldn't you want your own telescope? So we are proposing, my team at Arizona State, it's led by my colleague Patrick Young, who's an astrophysicist, and I may be the only biogeochemist who's ever been on a let's build a telescope proposal, but that's kind of cool. We're going to build we hope, if we can get the money, the Phosphorus Potassium Abundance Telescope. It's going to be a CubeSat. A CubeSat is tiny, right? This is a 3U CubeSat. It's 10 centimeters by 10 centimeters by 30 centimeters. Let's think about that. 10 centimeters is about the width of your hand by 10 centimeters by 30 centimeters. This thing is small. It's like the size of a box of cereal. This will be the first CubeSat proposal for astrobiology specifically. And the key to the proposal is that we're basically going to build a miniaturized high-resolution spectrograph that can look at the light from the stars, spread it out into its spectra, see where the absorbances are in the UV and the infrared for phosphorus and potassium. Remember, potassium also didn't have very many measurements. And a few other elements that are going to be important to understand for what rocks can form, whether or not biology has any potential to be involved. This is pretty exciting. And so we're asking a question that's fundamentally about looking for life in the universe. We're going to work with engineers and astronomers to build a really fancy telescope into a tiny space. And then if it all works out, it's going to get launched into space, and it will be in orbit around the Earth measuring phosphorus and potassium, which are the elements we need more data for, around in stars in the nearby, so shall we say, galactic neighborhood. So let's summarize this all. Chemistry is probably our best tool for detecting the presence of life, or not, on other planets. Phosphine on Venus was a detection of this chemical species that's super interesting. If it's real, we just dramatically changed our understanding of where there's life in our solar system. Though if you want my opinion, I think it's not looking good for our pal phosphine. I think it's probably sulfur dioxide. But it's still a really interesting example of how science works. We really need data for bioessential elements like phosphorus and nitrogen, and the rock-forming elements like potassium, calcium, and magnesium in stars and planets, because we're not going to have telescopes that can look and see trees or cells or DNA. We're going to have big picture signatures of the whole planet and its ecosystems. And so we want to build a telescope that's going to help us get more phosphorus and potassium data to help think about what stars and therefore what planets we should be looking at. So that's a lot of information in 35 or 40 minutes. I hope you thought it was interesting, and I'm happy to answer questions.
Thank you, Hilairy. That was very informative and very interesting. And we do have a couple of questions from our students. So, first question, could the phosphine be residual from bacteria that has died? How long does it take for it to break down?
Okay, so that's a really interesting question. Because it's toxic, the idea that the bacteria could have died is a really interesting one. However, if you look at Earth, we don't have any phosphine to detect, and that's because ultraviolet light, the same stuff that gives us sunburn, will break down the phosphine and cause it to react with water in the atmosphere and make phosphate. So we think that happens on the time scale of probably days to weeks. So if you can detect it in the atmosphere of Venus, it means it's been there for a while. And for a while means probably months to years. And so we scientists are reasonably certain that it doesn't stick around very long. And so that if it's there and you detect it, it has to be produced continuously to keep it in the atmosphere. So it could be residual, but we would expect it to break down from sunlight if it were present.
Okay. And question number 2, are there exoplanets that are similar to Venus where the sulfuric acid is not present, but the phosphine is?
Ah, that would be a fabulous question to know the answer to. Right now, we have not been able to measure the chemistry of atmospheres of exoplanets very many times. I think that there is 1 or 2 where we may have detected water vapor, but we don't have detailed chemistry about any exoplanet atmospheres yet. We're starting to have good information about exoplanets that are about the right size and are about the right distance from their suns to have potentially liquid water. But until we have much more powerful telescopes, we're kind of a long way from measuring chemical abundances in the planet atmospheres. But that's the next stage of the game, right? You guys who are going to be the future of science and policy and governance and all the other things that college students will become someday are going to be the ones who help solve those problems. But right now, it's going to be a long time before we can measure phosphine in an exoplanet atmosphere. But my gut reaction is there's so many stars, and we also now know there are so many planets, right? Thousands and thousands of exoplanets, that we could probably find examples of almost anything we can imagine.
Yes, that is a really good point. We're still early in the game, I would say. Question about the telescope. Building your own telescope, how much money are you hoping to raise to be able to make it? How do you plan to raise that money?
So it's a really good question. How much does the telescope cost? This is what you would call like a super cheap telescope. And the way we raise the money is we write a proposal to NASA, the National Aeronautics and Space Administration. They are the science research branch of the U.S. government, and they have a call for these proposals. And the proposal is to the tune of about $5 million, which sounds huge. But when you think about, you have to do the science, you have to do the engineering, you have to pay to have it built. It's made out of expensive materials like titanium and gold. But it's tiny, right? So that's good. To put it in comparison, the next big space telescope is called the James Webb Space Telescope. You might have heard of Hubble. That's the old space telescope that's been up for 20 or 25 years. James Webb is supposed to launch in a year or so. And James Webb is a $1 billion telescope with a B. So, and it's, enormous, and we'll see back to the very earliest times of the universe. So this is like a toy rocket kind of scale telescope. But it's also the future of satellites, right? Because if we can build them cheap and small, we could build a lot of them. Whereas a James Webb Space Telescope, you build one, it's taken probably 15 years to get it built. And it's going to be fabulous, but there's also only ever going to be one of them. So there's this movement afoot in space sciences to do miniaturized spacecraft so that you can do multiples.
That is so exciting. And are you building that telescope at ASU as well?
That would be super awesome. This one will probably not be built at ASU. We have partners at the Jet Propulsion Lab that will do the building. But there are people building spacecraft at Arizona State, and we're one of the only universities in the country that can actually build spaceflight hardware on site. So it's pretty cool.
And we have another question. If you could use that telescope that you're planning to build to look at is actually phosphine, there actually is phosphine.
Can you say that again?
Yes, if you could use the telescope that you are planning to build to look at Venus and confirm whether or not you have phosphine.
Oh, that's a really good question. I don't know for sure. The problem with looking at Venus is it's really close to our sun, and our sun is super bright. And so we have to use, and this telescope, the one we're building, its design is that it looks away from the sun. So it sits out beyond the Earth. The Earth is behind it so that it can look into space, and the sun is always behind it. But to look to Venus, it's hard because Venus is between the sun and the Earth. And so I think it requires a different setup and a different kind of telescope to do it. But we can go to Venus, right? It's not that hard. Granted, it's going to cost more than $5 million. But we should go to Venus with a probe that can measure it directly and actually try to measure it in the clouds.
Oh, that would be very exciting. Well, we have a crowd that is very interested in telescopes. How long will it take to build the telescope?
So if everything goes right, we think that we can build this telescope in about 3.5 years. And then it'll take another year or so to get it ready for launch. And by the end of a 5-year project, we should be making measurements of stars. The cool thing about the CubeSat is that there's nothing in the design that's unheard of. It's all relatively known technology, except that we're going to shrink the spectrograph down to be pretty small. That's the engineering challenge.
And then how long do you plan on gathering data when you build it?
For as long as we can.
Okay.
One of the limits will be if we have to cool it, because the detectors like to be cold. If we have to cool it, then there are some things that have to be added to it that will make it heavier, and that will cause its orbit to decay faster. But if it can be cooled passively, it will be lighter and it will last longer. But I think we imagine that its proposed lifetime is going to be on the order of 6 to 9 months. But if we could get a couple years out of it, that would be awesome.
There are many things that you have to think through for this type of projects. I can see that.
And I'm not the engineering expert, right? I'm on the science side of this project about why it's so important to make these measurements and why it's worth investing in an actual telescope to do it.
Well, we have a question about the science too. Does or can sulfuric acid act as a physical sunscreen for other elements, like phosphorus or potassium?
So the answer is yes, and this is because sulfate makes these aerosols that are reflective, right? The reason that Venus is so bright and white looking, what we call has high albedo, is because of the sulfuric acid clouds. They're highly reflective. And so it does limit the amount of UV radiation that gets into the clouds of Venus, for sure. And the model that they use to say how long those phosphine should last accounts for the sulfuric acid and the aerosol absorption of UV light. But that's a really good thing to think about.
Going back to the telescope, Erin asks, how will you get your telescope in space? Is that where NASA helps you get it up there? Just curious.
One of the nice things about the CubeSat program is that you propose to build the CubeSat and design it, and NASA will take care of putting it on a rocket and sending it into space. So we do not have to propose the money for launching it. But that's why it has to be a specific size, it has to be a specific weight or mass, because they send them up there in batches and they need to all fit into these little CubeSat launching packages, and they have to know how much it weighs, all that kind of stuff.
I'm curious about where do you find phosphine on Earth?
Excellent question. So you can't have it where there's any oxygen around because it reacts with the oxygen. So most of the phosphine we detect on Earth is found in what we call highly anoxic sediments, sediments with no oxygen, and we find those in wetlands. So think about like the sediment at the bottom of a peat bog. We don't have those in Arizona very often, but if you that smell of wet mud that is a little like rotten eggs, that's the smell of sulfide. And that is an indicator that there's no oxygen. And so it occurs when organic stuff that has high phosphorus breaks down in low oxygen regions. And mostly we think of that as happening in wetlands.
Another question, how long could we realistically have a lander on Venus' surface?
There was a mission to Venus that sent a probe, right? And that's where we got some of the pictures of the rocky surface of Venus. And it was designed to fall through the Venusian atmosphere. And I seem to remember, and I could be wrong about this, I'm certain somebody in the audience knows better than me, but I seem to remember that its lifetime at the surface was on the order of minutes. Because the pressures are quite high and the temperatures are kind of ridiculously hot. I mean, it's not melt rocks hot, but it's hot. And so most of our sensors and detectors and equipment isn't really designed for that kind of conditions.
But that's why we have these other ways to measure compositions of the atmospheres, right? So I have a question.
Yeah. And if you think it's really important to go to the surface of Venus, it's not impossible to design something that could survive, right? But it's challenging to design something that could survive that you could also get it there in a spacecraft, right? It can't be too big, it can't be too heavy, it can't be dangerous to launch into the atmosphere, into our atmosphere. There's all kinds of challenges. But if you have a good idea and a team of experts who are excited about that idea, you can write proposals to do lots of things.
Yes. And suppose you measure phosphorus and potassium with your telescope. What would be the next step to claim that you have evidence for life, that those elements actually are?
So there's a lot of steps between measuring these elements in the stars and claiming that there's evidence for life. A lot of steps. One way to look at it is to say, okay, do we even have all of the right ingredients to build a habitable planet, right? If you had a planet with no phosphorus at all, it would be hard to imagine life as we know it because we require phosphorus. Even our bacteria require phosphorus. It isn't to say that you couldn't speculate about life not as we know it, but that's much harder because we don't even know where to start. The potassium is interesting, right? Because it turns out the potassium is a source of very high energy radioactivity. And you need a planet, we think, that is dynamic, right? That has plate tectonics, that has a way to recycle elements, that has a way to move material from the crust into the mantle and back. And that is driven by the internal cooling of the inherent heat of the planet. And that heat comes from radioactive decay. And potassium is highly radioactive when it comes from when it is formed in stars. And we think it's really the main heat source for rocky planets. Uranium and thorium are also decaying and making heat, but those come in much smaller quantities from supernova, and not from the main star-forming regions where you can make potassium because it's lighter. So potassium is important we think, for making dynamical planets that have the ability to recycle things, plate tectonics essentially. And phosphorus is one of the key biological nutrients. If you didn't have those at all, or you didn't have enough of them, maybe you wouldn't focus on the planets for those stars. And so it's giving us a way to say, okay, these stars at least have the right ingredients. Let's focus on its planets. Because right now we don't even know where to start. We couldn't measure all the planets. That would be crazy.
Yes, and that is a very important point, that we don't have to think just about the living entities, but we have to think about the whole system, the planet being able to provide that life. Mm-hmm. And that is just beautiful. Mm-hmm. And we have two more questions. Let's see if we have time. When we say habitable, we mean life as we know it. Is it possible there is life as we don't know it out there?
Yeah, it's an important thing to sort of pause when we say habitable and think about that. For me, because I study life on Earth, I do mean life as we know it, because that at least I know what elements it's made of, what processes it might engage in. And I think at the early stages, when you're going to look for something, you may as well have a map to tell you how to get there, right? And so I think of the life on Earth as being a map to what life could be like in other places. But it's entirely possible that there's biochemistry we know nothing about. And it's entirely possible that there are other ways to think about life that maybe are based on how it processes information, how it enables complexity in the system. And there are definitely other researchers who are looking at different ways of conceiving of biosignatures that could tell us about life that doesn't exist on the Earth. This is why I don't like the definition of habitable as being just the presence of water. I think we have to think about habitability in a much broader sense, right? If your planet doesn't have the ability to recycle nutrients like nitrogen and phosphorus because it doesn't have a rock cycle, it's much more challenging to think about that planet, right? Mars does not currently have plate tectonics, and we don't, and that has real implications for what the surface of Mars is like, right? The surface of Mars is ancient, billions of years old, because it hasn't done anything in billions of years, except get hit by stuff that falls on it from meteorites. Whereas the Earth's surface gets recycled all the time. And so I think that presence of a plate tectonic cycle is really important. So I think we need to broaden the definition of habitable. Actually, I'm going to say one more thing. The habitable zone says it has to be liquid water at the surface. That means that by the NASA definition of the habitable zone, Europa and Enceladus and these moons around Jupiter and Saturn that have oceans underneath are not considered habitable planets. Their surfaces are fully frozen. There's no liquid water. But I think those bodies are some of our best potential for seeing possible ecosystems on other planets, because they have liquid water with a heat source at the bottom of the ocean.
That's right, yeah. And speaking of Jupiter, tonight at 7 p.m., if you join us for A Night Under the Stars, you'll have the opportunity to see Jupiter, Saturn, and Mars today on our Discovery Day. So Hilairy, thank you so much for this very interesting, stimulating hour. Do you have any closing remarks?
I would like all of you guys to think that there's a place for absolutely everybody in how we're going to explore our solar system and our universe. Even if you're not a physicist, even if you're not a chemist, even if you're not thinking about how to build a telescope, you know, all the things we do in order to enable science is the entire range of the human experience, right? There are project managers and attorneys, and ideally there would be writers, because let's face it, some of the stuff that comes out of NASA is written really badly. And so you don't have to be a scientist or an engineer in order to be excited about how we're going to explore the universe, right? We need people who are creative and smart and interested in the world around them from all disciplines if we're going to explore the universe. So I hope there's a little piece of this for you, even if you are thinking about human health or, you know, public policy.
Yes, or even planetary health, right? So
or geochemistry.
Yes, biogeochemistry. Well, thank you so much. I want to thank our audience, and I want to thank also our tech production and Dr. Mike Santoro for moderating the chat along with Tyler. And again, thank you, Hilairy, for joining us today. And stay tuned for tonight's A Night Under the Stars.
It was delightful to be here. Thank you for inviting me.
That's a pleasure. Thank you.